Hi guys, this is Mrs. Gastler, and in this video we're going to talk about rotational dynamics. It's kind of got two pieces plus a little bit about problem solving. So we've got, the first thing we're going to talk about is torque. Torque is sort of like force, but not exactly like force. And we'll probably talk a little bit more about this in class, but torque is this interesting thing. It happens when a force is acting on something called a lever arm, which is sometimes called a moment arm, which is kind of a weird name for it. But what happens is you have some sort of object, and when you push on a point on it with a force, and it is able to pivot around some point. So there's some sort of axis right here, with the point P. This is our axis. Okay, there's a radius right here that it goes out to this point where the force is applied. And that force is going to cause this object to rotate about that axis, okay? And that force is causing a torque to make this object rotate, okay? A force acting on a lever arm, it makes things rotate, okay? So according to how we are able to calculate stuff with our somewhat limited what do you call it? Mathematical skills here in Algebra 2. So the symbol that we use for torque is this is the Greek letter tau, T-A-U. Okay, it's lowercase. It looks like sort of like the T that I write for time, but I left the top off. Okay, it's a lowercase. And what it is it's R times the perpendicular, or it's the perpendicular component of R times F, okay? In some more advanced math classes, whoops, this tau is R crossed into F, if these are vectors, okay, the cross product. But we don't really know how to do that yet. But the way that you would do that is the same as we're going to find the perpendicular part here, okay? So if we were to like draw some arrows on it, okay, R perpendicular to F is going to be R sine theta, okay? R times the sine of theta is where that's going to be put in there. So F is actually going to be this way. Is that how it goes? Yeah. No, it's this one, okay? R sine theta times F, okay? Times F. So this is what we're going to do. So RF sine theta, usually we write that RF sine theta. R sine theta is actually what's called the moment arm. So if a question says, what's the moment arm? R sine theta is what you're looking for, okay? So torque is this way. So sine theta is the one that starts at the axis and goes up. So if it is parallel, if the force is parallel to the radius, there is no torque. So if I push this way or if I push out, I pull out, I'm not going to make the object rotate. And that would be here and here, so that's going to be what's happening there. So I'm going to get the biggest torque if I go perpendicular, okay? So if my sine of 90 is there, okay? So that is the basics of torque. As far as direction goes, there's this right-hand rule that helps us do that, but that takes a lot more calculus, and I don't think you're going to have to do that on the AP Physics test because we don't know calculus, okay? Now let's talk about Newton's second law. In rotational motion, okay? So we've been doing a bunch of equivalents already, right? We had omega instead of V and alpha instead of A. And now we're going to use force instead of torque, but we have to add a little bit, or torque instead of force. So F net equals ma is our linear Newton's second law. Written this way, but instead of F net, we're going to have the torque net, which would be the sum of all the torques, right? And instead of A, we'll have alpha, but instead of mass, we have to have this other thing, okay? This is mass, okay? We have to have, so mass, what mass does is mass resists acceleration, okay? We call it inertia, right? In rotational motion, we don't, the mass is kind of weird actually. And we'll take a look at this later, but if you have mass and you're trying to rotate it, the further away from the fulcrum, that changes how easy or hard the mass is to rotate. And so we have something called rotational inertia, and that resists rotational, that's an O, acceleration. Okay, and so that's what we're going to be putting in here instead of mass. We're going to use rotational inertia. So we have mass here, rotational inertia here, and rotational inertia is given by the letter I. Okay, not impulse I, I for rotational inertia. Okay, so this is our rotational equivalent of Newton's second law. And you can use it in much the same way. So if I have some torques that are trying to rotate things in opposite direction, if the net torque, so this is the first law equivalent, so first law, okay, if F net equals 0, then the acceleration is 0 and the object does not change what it's doing. In a similar manner, if torque net equals 0, then the object doesn't accelerate as it's rotating. So it might be rotating at a constant speed, but it's not going to accelerate as it's rotating. Or it might be not rotating at all, okay? But it's not going to change. So these have some very similar things. There's also a third law equivalent for every torque this way, there's a torque that way kind of thing. So for every action torque, there is an equal and opposite reaction torque. So if you've ever tried to spin something and found yourself spinning in the opposite direction, that's what you are experiencing, okay? So let's talk a little bit more about rotational inertia. So perhaps you have seen, so this is again the equivalent of mass. Inertia resists acceleration, and rotational inertia resists angular acceleration. So there's a bunch of different ways that you can think about this, but what you need to know for rotational inertia is that to find the rotational inertia of a system of particles, right? System of particles. The moment of inertia would look like this. Sometimes they call rotational inertia moment of inertia, which makes it sound like it's in a particular place, but that's really not it at all. Moment of inertia is just the same thing. So what you're doing is you're taking the sum of, right? This means the sum of the mass of all the particles times the square of the radius of the particle. So you're going to do mass of this particle times the square of its radius plus mass of this particle times the square of this radius plus mass of this particle times the square of this radius. That's how the summation works. So m1 r1 squared plus m2 r2 squared plus ... however many you have, okay? This would be for particles. That's enough. For particles. So if you have a system of particles, that's what you would do, which a lot of times you can think of it as a system of particles. If you were to take calculus-based physics, you would learn how to do some really great integral calculus to find the moment of inertia, the rotational inertia of an object based on its shape. And its mass density, which is all sorts of fun. But you don't have to do that. If you look in your textbook or a copy of the textbook on page, or you can Google it on page 208, there are some formulas for various shapes, okay? some shapes that are useful, but that you don't have to really memorize. I think most of the time it's going to give you some shapes for the eye. I can't remember if it's on the equation sheet, and I don't see one close enough that I can reach. But if you have like a stick on the end of a rod, so maybe this is able to go around that way. So this is the axis, okay, and it has a length L. Then the moment of inertia for this is 1/3 ml squared, okay? So you'd have the mass of this rod times the length times 1/3, okay? There's also spheres, okay? So if you have a like Earth, okay? So it has a radius, right? Okay, so the rotational inertia of Earth is 2/5 m times the radius of Earth squared, okay? So we can find all sorts of interesting things about the rotational inertia. And then these values is what we're putting in here. Now, an interesting thing, a note about units, okay, and torque is the first one I want to make a note of. When we do R times F times the sine of theta, we're going to have meters times newtons. And this is not a joule, and it's really annoying. The reason the meters is there is because our angular velocity and our angular acceleration is using for a displacement the unit of radians and degrees, okay? Theta, meters, it's not meters per second. The displacement has essentially no unit. And so in order to get to energy and power and work and all that stuff, which is in joules, we have to have an actual distance unit in there. And so this is why the displacement unit is in the torque. But that doesn't mean that this is being measured in joules. Torque is not measured in joules because it's not energy. It's not energy, okay? So we don't call it a joule because it's not energy. We call it a meter Newton instead, which is, it might seem silly, and that's okay. You just kind of have to be okay with that. For the moment of inertia, you'll see that it's kilograms times meters squared, which doesn't have a special name or anything. But when we put this times our, times the, combined with the alpha, which is radians per second squared, that's going to allow you to get to the right unit for other things that you're measuring, okay? For the torque, and that's going to get you the torque unit when you do this equation here, okay? Because you're going to have meters, which is going to get you the meter in front. Where'd it go? Meter in front, and then you're still going to have newtons, so you're going to get meter newtons out of that. And then later, when you're trying to find the kinetic energy, the rotational kinetic energy, which we'll do, I think, in the next video, then you will have the joule, okay? So that's how that works out, which might seem weird, and that's okay. And that's all I have to say for right now. When you are solving problems, it works the same way as linear, okay? It works the same way as linear. You probably want to draw some pictures and think about what you know and what you don't know. Make sure you keep your directions consistent. So like rights and lefts are going to be kind of weird. If you go counterclockwise and clockwise, that's going to be a lot better, okay? If you have something that is not moving, you're going to want to be using these things here, okay? Just like you were. Sometimes you might have translational. They call this translational equilibrium, and they call this rotational equilibrium. And so if you see those words, then you know these things are true, and then you can use that to solve your problems too. There's some problems that you can work on. Let me know if you have any questions. Thanks for watching.